So we're going to focus on particularly the three physical things here that you need to do for the DNA: to copy it, to distribute it, and then really to just physically separate it and divide it during cytokinesis. And today we're going to begin with the process of DNA replication. So if we're going to distribute it, we need to really make sure that we're making an exact copy. And I'm going to bring out my pool noodles for this. So these, for the beginning part of the lecture today, these are going to serve as our chromosomes. So if you imagine you have a long linear unit of DNA, there's going to be different parts of that chromosome that we're going to come back to. But we have our chromosome. The ends are the telomeres, and the chromosome itself looks like a great chromosome. We have this chromosome. It's functioning perfectly well in that beginning cell. But now we need to come back and make a new copy of this, two exactly identical copies, each of with the complete genetic material that we can use to distribute to those two new cells. Okay. And in order to achieve this, there's going to be several key things that we need to do. So we need to be able to make sure that we copy the DNA once, but only once. So for example, if we were to make 3 copies of the DNA, that'd be really problematic. We could start getting imbalances in the way that our genes are being expressed. It can be quite problematic for a cell. And in fact, many cancer cells are typified by having abnormal copy number of some of the chromosomes, either through errors in replication or errors in chromosome segregation, as we'll come back to. So we need to achieve this. We need to do it. If we don't do it, we will not have genetic material to distribute. If we do it more than once, it's a problem. And so we need a scheme that's going to be set up to really precisely ensure that you do it, but only once. Okay? And we're going to have 3 separate phases of being able to achieve these. These are temporally separate phases, but also highly regulated phases. And the first thing that we need to do is define what part on this chromosome we're going to be able to start to copy from. So if we're going to bring in a polymerase, it's very hard for it to access the DNA. We actually have to unwind the 2 strands of DNA so that the DNA polymerase can access that. And the site on each chromosome where we're going to do that is going to be called an origin, a beginning. And so if you're going to copy it, you have to start someplace. This is going to be referred to as the origin. Okay? And we have to have the cell come in and mark and identify those places and say, hey, they're good to go. Okay? So we're going to begin by licensing these origins. And imagine a little bit like your driver's license. Here is the permission the cell is giving you to be able to say, you're good. You have the capacity to start driving when it's time for you to start driving. And so in the same way, it's going to have to mark these sites on the chromosome and do that in a defined way. And this is actually going to happen in a regulated manner. We're going to come back to this when we discuss the cell cycle. And this can occur only in this G1 phase, only during this period of growth. And we'll talk about the regulatory control of this in this next lecture. Okay? So we got to license these origins. So this is happening only in G1. And we're going to essentially mark the sites to begin DNA replication. So this can be a hard thing to achieve for this chromosome. Our chromosomes are huge. And DNA polymerase is a great enzyme, it's a great machine, but it's going to take a while to be able to do this. And so instead, just defining one place in this where you can begin replication and move in both directions, really what the cell is going to do, particularly in some of the larger cells that exist, is to define multiple sites. So in the case of an E. coli chromosome, bacterial chromosome, there's just one origin, just one beginning point. But in the case of most eukaryotic chromosomes, you're going to be able to define multiple origins. And actually, the frequency of these is going to make a big difference in how long it takes to replicate the DNA. Of course, if we had 1, it could still happen, but it would take a long, long period of time. If we had 1,000, it's going to occur much faster. And if we had 10,000, even faster. So I think the order is probably on the level of maybe 1,000 per chromosome for most human chromosomes, but actually do not know the precise number. Okay? So we've marked these sites. We're going to now have to come back and actually act on them. And so this is happening in G1, the marking of the sites. But now we're going to have to fire the origins. Okay? So we've started with the licensing process. Now we're going to fire them. And this basically says we're going to trigger them. We're going to get that origin to unwind the DNA. and start replication. Okay. So this really is the business end of replicating our DNA. And again, this synthesis process is going to happen during S phase. And then finally, we want to make sure that this happens. And so we've set that up to achieve this. But it only happens once. And so once these origins are fired, once they are triggered, they cannot happen again. They cannot be reset to repeat this until the next G1. Okay. And so we have the scheme now in place that we can come through and copy these units of DNA.